Good day, everyone. My name is Lindokuhle Dlamini, and I'm here to share to you a section of my PhD that looks at carbon storage in montane fire climate grassland, the battle between trees and grasses. Grasslands are the second largest biome in South Africa, and they have high plant diversity and they provide many ecosystem services. Often grasslands do need some form of regime of disturbance to maintain the dominance of grassy layer. That's why grasslands are often seen as secondary in nature. However, there is huge evidence that shows that grasslands are actually ancient and they are primarily grassland. However, they need fire, or they are at equilibrium with fire, and they are primarily in their nature. Because grasses are not woody and grasslands are assumed to be secondary in nature, a large focus when it comes to climate change mitigation and carbon sequestration have been on trees and forest. You've heard a lot about the Amazon burning and the tropical rainforest. So this therefore neglects the large quantities of carbon that is stored in the soil. Soils are the largest reservoir of terrestrial carbon. They store 4 times the carbon stored by above ground vegetation. They store 3 times the carbon that is stored in the atmosphere. So soils are actually where we should be focusing on. In South Africa alone, grasslands store about 60% of the national carbon stocks. And within that 60%, about 90% of the carbon is found in the soil in the form of soil organic carbon. So this shows how important it is to understand the dynamics between fire and vegetation, different vegetation or vegetation heterogeneity, and the storage of carbon in these regions. The good thing is soil organic carbon is gaining interest globally. One of the reasons for this is the hope that improving soil management through effective land management and restoration may capture significant amount of carbon from the atmosphere and sequester it into the soil. But this has led to challenges like the Bond Challenge, the UN Trillion Trees, that wants to plant trees even in montane grasslands like those in the Drakensberg. This then brings me into my aim and research questions. I aim to determine the effect of fire and land degradation on soil carbon storage in montane fire-driven grasslands. I ask really simple question. Does fire exclusion lead to greater soil organic carbon storage? What is the effect of land degradation on soil carbon storage? This study is conducted in Drakensberg, Cathedral Peak long-term trials. Around the 1940s, the Department of Forestry in South Africa wanted to investigate the effect of fire and afforestation on water delivery. They then found catchments that were primary grassland. They planted them with pine, and then after planting them with pine, they realized it's affecting stream flow, so they cut down pine. After cutting pine, it changed to a catchment that is dominated by bracken fen. Bracken fen doesn't have basal cover, so there's a lot of soil erosion. The other catchment was converted into a fire exclusion catchment, and it got dominated by woody plant species. So we now have 3 catchments that we work in. Catchment 3, which is degraded, dominated by bracken fen. Catchment 6, which is a natural grassland that is bent every 2nd year. And catchment 9, which is a fire exclusion catchment dominated by woody plants, especially Leucaedia. So we went to these catchments and we collected soil samples at different depth interval and different slopes, top, middle, and bottom. And we used this auger, which doesn't disturb the soil further, but allows you to collect undisturbed soil cores. So one of the key things that we are looking at is carbon distribution in the topsoil. and looking at the fire excluded catchment, comparing pioneer forest and adjacent grassland in carbon stocks, active carbon, and carbon isotopes. And then we look at the natural grassland versus the degraded catchment in top, middle, and bottom slope in their stocks and active carbon. Carbon distribution in these catchments is really interesting. We looked at fire excluded catchment. Carbon distribution in this catchment is relatively evenly distributed, but there is more carbon in that catchment compared to the other two catchments. This could be because this catchment is south facing, so it's cooler, it receives more rainfall compared to the other two catchments. The other two catchments have no significant difference between each other, but the natural catchments have slightly more carbon than the degraded catchment. What was interesting was the degraded catchment have more carbon in the accumulation zone or in the bottom slopes compared to the top slope, which shows the evidence of organic matter being transported. The natural catchment shows that carbon is evenly distributed. When we zoom in closer to the stocks in catchment 9, which is the fire excluded catchment, we are seeing that stocks are higher in the pioneer forest compared to the adjacent grassland in the top 0 to 5 centimeter. But as you go down the depth, you are seeing that the grasslands, the adjacent grassland, stores more carbon than the pioneer forest, and this is stocks, so it takes into account depth and it takes into account bulk density. So what this graph and this figure is showing us is the importance of subsoil carbon stocks, and that grasslands actually store more carbon. When we look at active carbon, which is carbon that is susceptible to being released to the atmosphere because of soil respiration, you are seeing that even though pioneer forests have more carbon in the 0 to 10 centimeter, it actually have more active carbon also, which means the carbon that is available is susceptible to being released to the atmosphere. Both these adjacent grassland and pioneer forest have more in the 0 to 5. This is normal, and active carbon decreases with as you go down the depth. That is normal. But what we should note is these values of active carbon are high. They are really high in these mountain regions. When we go back to the question that we want to answer, does fire exclusion lead to greater carbon storage? We have to first look at where does the carbon in the soil come from. So to understand that, you look at C4 and C3 plants. C3 plants are trees mostly, so pioneer forest, and C4 plants are mostly grasses. But in these montane grasslands, you are finding also other grasses which are C3. So C4s are around -12, -13, and C3s are around -28, -27. So what we are seeing from our graph is the values show that they are around -23, not -28. So what does this show in the pioneer forest? It shows that the contribution in the carbon comes from both grasses and trees. So there is a mixing. Same with the adjacent grassland. You are seeing it's -17, and then it goes down to -14, -15, but it's not entirely -12. So it shows mixing of the carbon or mixing of the contribution of carbon from different vegetation types. So to answer our question, does fire exclusion lead to greater carbon sequestration? No, it doesn't. It doesn't. We are seeing that actually grasslands or adjacent grasslands have more carbon than the pioneer forest. When we compare the natural grassland or semi-natural grassland, which is catchment 6, and the degraded grassland or degraded catchment, which is catchment 3, that used to have pine and it got removed. So we are seeing that there is evidence of soil being transported, and that soil carries carbon with it. So you are seeing in the top slope, the natural grassland or natural catchment have more carbon in the top soil, more carbon. You are seeing more carbon, as you would expect, because a lot of carbon gets transported to the bottom slopes. In the middle slope, you are seeing not a lot of significant difference. So obviously some of the carbon in the degraded catchment gets transported down the bottom slope, but some gets accumulated into this catchment. So you are seeing that there is not a huge difference, but there is a difference as you go down the depth. But what is interesting is in the bottom slope, in the topsoil, there is not a huge difference in terms of the stocks. But as you go down the depth, you are seeing that there is layering, there is accumulation of carbon, and that carbon that is accumulated gets protected. So that's why you are seeing more carbon as you go down the depth in the degraded catchment. So it shows the transport of soil that carries carbon with it. When we compare now these two catchments in terms of their active carbon, the susceptibility of the carbon in the soil to respiration, you are seeing that the top slope and the middle slope, there is not a lot of difference. There is not a significant difference, not a huge variation in terms of these two catchments. But what is interesting is in the bottom slope, you are seeing now all the carbon that is transported, all the topsoil that is transported down the slope into the bottom slope. You are seeing now, it's showing now that carbon is not stable. It's actually active. It's susceptible to respiration. So there is a huge difference between the natural grassland and the degraded grassland. So the carbon, even though it's transported down, it's susceptible to being released to the atmosphere. To conclude, these findings are showing us that forest or pioneer forest in montane grasslands, montane high rainfall grasslands, do not store more carbon in the soil than the adjacent grasslands. So forests do not store more carbon than the adjacent grasslands. These findings are similar to those that we're looking at bush encroachment and correlating it with rainfall gradient. Grasslands that are found in high rainfall areas generally store more carbon than the adjacent trees or adjacent forest. Also, these findings are showing us that after planting trees, when you remove them, that results in soil organic carbon transport, and the carbon that is found in the bottom slopes is generally susceptible to soil respiration. Therefore, planting trees in well-managed montane grasslands might lead to soil erosion and soil organic carbon loss. I thank you so much.